over the course of the next 2 weeks, we'll be talking about rates of reactions and how that can apply to systems in equilibrium. And also, when we talk about equilibrium, we're going to be learning about Le Chatelier's principle and how to predict which direction the equilibrium will shift. So just a quick review. In class this past week, we've discussed things that can affect, or the factors affecting, the rate of a reaction. So if we increase the temperature of a solution, the reactants will collide with each other quicker, causing the reaction to occur faster. So that means that it increases the rate. The same thing is true for increasing the concentration of one or both reactants, for stirring the solution, for increasing the pressure of a gas mixture that is having a chemical reaction occur, or through the addition of a catalyst. And the catalyst does this by lowering the activation energy. So that's just a quick review. And also, we want to see how we can change the reaction into something called the rate expression. And this is very much simplified, but one way that we can write the rate expression, or at least predict the rate expression for a reaction, is as follows. The rate of this reaction, we're just going to use this one as an example, would only depend on our reactants. So we're not going to care about the product, only the reactants. And we take the substance itself, so N2, and we're going to put it into brackets. There's 1 mole of N2, and we know that because it does not have a coefficient, so we would put the exponent as 1, which you don't have to write because it doesn't actually change your number, but I just want to use that for demonstration purposes. And then we put the second reactant into brackets, which is H2. And since we only have 2 reactants, we're only going to have these 2 terms. But the coefficient of H2 is 3, which means my exponent would be 3. And the only thing we forgot from our rate expression is K, which is our rate constant. And don't forget, if we have brackets around a substance, the brackets represent the concentration, which would usually be in molarity. So let's do the example below using our rate expression. Calculate the rate of the above reaction when the concentration of N2 is equal to 0.062 molar and the concentration of H2 is equal to 0.045 molar if the rate constant is as follows. Okay, so we're going to just plug these things in. So we're supposed to calculate the rate. That means rate is our unknown. I'm told my rate constant is 1.3 times 10 to the negative 5th times per second. That's what seconds to the negative 1 power means. Then my concentration of N2 is 0.062, and that doesn't really have an exponent. And my concentration of H2 has the exponent of 3rd power. So according to our order of operations, we want to take this to the 3rd power first. So let me get a calculator. 0.045 raised to the 3rd power gives me 0.0000, it's a really small number, 91. I'm just going to keep 2 sixes there. Times 0.062 times 1.3 times 10 to the negative 5th power. And that all should give me my rate. So I'm going to take these numbers and multiply them. 0.062 times, 1.3 times 10 to the negative 5th. All right. The answer I have calculated is 7.3 times 10 to the negative 11th, and the unit would be molarity per second. So it's the amount of concentration that reacts per second, and that's the rate at this concentration with this rate constant. Okay, so that's an example of how you could calculate the rate, which we would call the instantaneous rate, at these concentrations. All right, so when talking about the rate of a reaction, it's important to keep in mind that reactions can actually be going in the reverse direction. And to indicate that, we have this double arrow. So nitrogen gas is reacting with hydrogen gas to produce ammonia, NH3, but it's also having some of that NH3 reconverting back into the reactants. And so the reverse reaction I've written out below. NH3 can produce some N2 and some H2. And it's whichever direction has a more significant rate of reaction is going to react a lot faster than the other direction. So if we wanted to do this, we could write the rate expression for this reverse reaction. So the only reactant I have on the reverse reaction is whatever was our product before. So the rate for this one would be rate equals K times the concentration of NH3, and it doesn't have an exponent because it doesn't have a coefficient. So this would be the rate expression for the reverse reaction. And depending on whichever rate is smaller, will tell us in which direction or which side will have a higher concentration at what we call equilibrium. And equilibrium is something that occurs when the forward and reverse rate of the reactions are equal to one another. So that means that product and reactant concentrations remain constant at equilibrium, because just as much reactant is trying to form product as product trying to go back to reactant. Alright, so an example of this is shown in this image with the water buckets. So to start out, there's way more of the product example. The second bucket would usually be on the right side here. It's on the right side here, so that could represent the product. So there's way more of the product here, and it's forming reactant, meaning that the water is traveling into this bucket because this bucket is not filled up past the energy level where the water is coming through. Okay, so once it reaches equilibrium, the amount of water that's traveling in this direction and in this direction is equal, which means the level of the water stays constant. Alright. Now, when we look at the second example here, we have an example of diffusion, which is the same general idea, where when all the concentration is on one side, they will try to equalize between these two sides if they have the opportunity. And so these particles will move into this side, and once particles are on this side, they may start to move back the other direction, but until they have equilibrated, where there's an equal amount on either side here, they won't be going at an equal rate necessarily. So this would be considered an equilibrium because just as many particles could make it through this direction as this direction at the same rate. Alright, so just to restate, our equilibrium is when our forward and reverse rates are the same. The amount of reactant and product will depend on what the equilibrium constant is in the relative concentrations of each reactant or product. Okay, but in general, we can see these graphs and how this would relate to equilibrium. So like I've said, our reverse rate is usually a lot smaller than our forward rate starting out, but as the reactant starts to produce product, the rate will decrease, and as our product is formed, the rate of the reverse reaction starts to increase because there's more products that could go back to reactant. And eventually they become equal to each other, so this purple line represents the point where they're equal. So here is where the equilibrium begins, once they have equal rates in the forward and reverse direction. When we talk about the concentrations at equilibrium, the reactants may, the equilibrium constant could be so that product is favored at equilibrium, which would mean there's more product at equilibrium. This may not be true, but it depends on the reaction. So in this graph, there's more product. That's why the blue line is higher. There's more product at equilibrium than reactant, but the amount of reactant and product are not changing anymore. They're staying constant. That's why the line is flat. So we can calculate these things and be able to draw a graph of this sort using something called the equilibrium expression. And this is set up like it shows here. The equilibrium constant, KEQ, is equal to the concentration of products. Okay, so pay attention to that. Product goes on the top, divided by the concentrations of reactants. So our reactants go in the denominator. And since A in this reaction does not have a coefficient, it doesn't have an exponent. Same is true for C. It doesn't have an exponent. But B has a coefficient of 2, so it gets an exponent of 2. Okay, so your web assign may be asking you to set up the equilibrium expression. And once you put the chemicals into the brackets, that's all it's asking you to do. Just set it up like this. Now, if our equilibrium constant is greater than 1, that means that in order for this fraction to give you a number greater than 1, the stuff on the top has to be bigger than the stuff on the bottom. So that means the reaction favors products. There's a higher concentration of product than there is of reactant. Okay? Alright, so then if the equilibrium constant is less than 1, that means that the number on the top is smaller than the number on the bottom. And that means that your reaction favors reactants. So you would have a higher concentration of reactants. Alright, and this one was for product. Alright, so let's try this example. If we want to take this reaction, sodium carbonate reacting with calcium chloride to produce calcium carbonate and sodium chloride, we can change this into an equilibrium expression as follows. KEQ will be equal to, remember our products go on top, so that's this side. So I'm going to take concentration of calcium carbonate, and it does not have a coefficient, so no exponent, times the concentration of sodium chloride. And it has an exponent of 2 because there's a coefficient of 2. Sorry, that went off the screen just a little bit. All of that is going to be over our reactants, which are the other ones. So I've got sodium carbonate, Na2, sorry, I've got 2 down here, CO3. It does not have a coefficient, so it does not have an exponent, and neither does our calcium chloride, our other reactant. So this would be our equilibrium expression, and that's all I was asking us to do for writing our equilibrium expression. Okay? Alright, so we are going to discuss Le Chatelier's principle in the next video, but this is basically if you change something about your equilibrium state, how can it restore equilibrium? So we're going to discuss that in a little bit more detail in the next video.